right now. We're going to take a deep dive into surface area and volumes. Think of these as the mathematical blueprints that actually let us decode and, well, construct the physical world around us. I mean, from the staggering scale of the Great Pyramids all the way to the sleek glass of a modern skyscraper, the formulas we're about to explore are basically the invisible rules that govern physical space. It's really cool stuff.
Here's a quick look at our roadmap for today. We'll start with understanding 3D space, move into cuboids and cubes, then cylinders and cones, hit spheres and hemispheres, and finally we'll wrap up by combining solid shapes.
All right, part 1. Understanding 3D space, the foundation.
To really ground us today, consider this quote from our source text. Understanding solids begins with knowing their surface and space. It's a beautifully simple starting point, right? To truly grasp the geometry of the physical objects all around us, we have to master two primary concepts: the outer boundary that wraps the object and the space hidden inside it.
Okay, let's dive into this with a quick, elegant refresher. In geometry, we step from flat, two-dimensional planes, stuff defined entirely by just length and breadth, straight into the real world. It's that all-important third dimension, height, that literally brings a shape off the flat page and into our reality.
When you're trying to understand these 3D objects, it basically all comes down to wrapping paper versus water. Surface area is just the total area of all the outer surfaces of a solid object. It tells us exactly how much space the surface covers. Like how much wrapping paper you'd need for a gift. Volume, on the other hand, well, that's the amount of space actually occupied by that solid object. It tells us the capacity. Basically, how much water the solid can hold inside. Moving on to part 2, cuboids and cubes. Let's talk about the boxy shapes. Take the cuboid, for example. Its vertices, faces, and edges are all defined by length, breadth, and height. Now, if you make every single edge completely identical, boom, you lock into a perfect cube. Just think about the everyday geometry we totally ignore. Like, a standard pizza box is really just a wide, flat cuboid holding a cylindrical pizza that's eventually cut into triangular prisms. Mind-blowing, right? Anyway, let's turn these visual anchors into actual math. So, for a cuboid, calculating the total surface area means you've got to account for all 6 faces. That's the floor, the ceiling, and the 4 walls. But for our perfect cube, the math simplifies so beautifully here. Since every single edge is exactly identical, the lateral wrapper is just 4a squared, the total shape is 6a squared, and the volume, that's simply the edge cubed. It's super clean.
All right, part 3. Cylinders and cones. We're entering the curves now.
When we introduce curves, like with a right circular cylinder, we can't rely on length and width anymore. Our fundamental tools shift entirely to the radius of that circular base and the straight vertical height. From here on out, absolutely everything we calculate stems from how this flat circular base interacts with that vertical height.
And here is exactly how they interact. The area of the base is just your standard circle area, right? Pi times r squared. But to get the curved surface area, basically that wrapper around the cylinder, you just take the perimeter of the circular base and literally stretch it upward by multiplying it by the height. If you want the total surface area, you just slap the 2 circular ends back on, and finally, to find the volume or the capacity, you take the area of the base and multiply it straight up by the height.
Now, what's really interesting about this slide is this brand new variable, L, the slant height. As we move from a straight cylinder to a tapering cone, a standard vertical height just isn't enough to calculate the outer surface anymore. We need the slant height, which is the diagonal distance down the side of the cone. And thanks to the trusty Pythagorean theorem, it's easily calculated as the square root of height squared plus radius squared.
You can clearly visualize it here. See how the vertical height drops straight down to the center, while the radius forms the flat base, and that crucial slant height runs right along the angled outer edge? These 3 components form an absolutely perfect right triangle right there inside the cone. Let's look at the formulas and see how this builds our understanding. For a cone, the curved surface area completely relies on that slant height we just learned about. It's calculated as pi times r times L. The total surface area, that just adds the pi r squared base right back to it. But look really closely at the volume for a second. The volume of a right circular cone is 1/3 pi r squared h, meaning it is exactly 1/3 the volume of a cylinder with the exact same base and height. I mean, what a fantastic mathematical relationship.
Let's hit part 4, spheres and hemispheres, purely curved.
For a perfect sphere, life gets surprisingly simple. There is no length, no breadth, no slant height. The radius, r, is the single dimension that dictates absolutely everything here. The total surface area is an elegant 4 pi r squared. And the volume, the total capacity inside that ball, is 4/3 times pi times r cubed. Literally, one variable unlocks the entire shape.
But watch what happens when we cut that sphere right in half to make a hemisphere. The volume behaves exactly as you'd expect, right? It drops perfectly in half from 4/3 to 2/3 pi r cubed. But the surface area? And this brilliantly illustrates the nuance of geometry. The curved surface area halves to 2 pi r squared, sure. But slicing that sphere just created a brand new flat circular base. So the total surface area of a hemisphere has to add that new base area in, resulting in 3 pi r squared, not 2. Actually, let me emphasize that. You always have to account for every exposed surface.
Finally, part 5, combining solid shapes, the synthesis.
Think about this for a second. Very few objects in the real world are a perfect isolated sphere, or, a perfect isolated cube. A storage tank might be a cylinder with 2 hemispherical ends. A circus tent might be a cylinder topped with a cone. So what happens to all this math when these basic solids combine?
So the crucial point here is this master rule. Calculating the volume of a combined solid is actually incredibly straightforward. The total volume is simply the sum of the volumes of each basic solid. You literally just add up the internal capacities. But surface area, well, that's a bit tricky. The total surface area of a combined shape is the sum of the curved surface areas of the individual solids. Why? Because when you stick two shapes together, their connecting bases are suddenly hidden inside. You only calculate the area of the surfaces that are actually exposed to the outside world.
That rule really changes how you view the physical world, doesn't it? You now possess the formulas to decode the capacity and the boundaries of almost anything around you. So I'll leave you with this thought. The next time you walk past a towering building, or honestly, even just look at a simple plastic storage container in your kitchen, how many basic solids can you break it down into? Your toolkit is ready. Keep observing, keep calculating, and hey, thank you so much for joining me on this explainer.